Hello dear viewers, I will be continuing with my presentation of measuring radiation burden using MIRD method, medical internal radiation dose method for internal dose calculation. I'm using a different format this time and I hope that you like this too. From this picture, you can see various human models of different sizes and of both the genders which are used for internal dose calculation using MIRD MIRD method. The contents of this presentation will be the basic concepts of MIRD method and the different parameters used for internal dose calculation like cumulated activity, effective half-life, and residence time. The main point of absorbed dose in which there is a value, S value, what is it? And the tomography for dose calculation of specifically the patient using their tomographic data and making it more accurate, tailor-made, and personalized. Finally, I will summarize the contents, show you the references, and leave you with a parting question as usual. Now, the medical internal radiation dose method is used to calculate dose to a particular target organ from radioactivity present in one or more source organs in the body in general. Why in general? Because it is the humanoid models that are being used to calculate the internal radiation dose and extrapolate to the individual or the patient whose internal dose calculations have to be made. Now, the requisition for internal dose calculations, cumulated activity in the source organ and which is inside during the residence time, the energy emitted per disintegration in the source organ, the mass of the target organ, and the absorbed fraction, that is what I had explained in the last presentation, energy absorbed by the target organ upon energy emitted by the source organ per transformation of radioactivity in the source organ. Now, this absorbed fraction is based on the size and shape of the source as well as the target organs, anatomical relationship of the target and the source organ, that is, how far are they from each other and which one is above the other. These things are what the absorbed fraction depends upon. The type and energy of the radiation also affects the absorbed fraction. Now, to calculate this absorbed fraction, for each source target organ pair, energy and type of radiation using humanoid models like this, the reference man of average shape, size and shape, and using the Monte Carlo technique algorithm. And these data have been published by MIRD in the form of MIRD pamphlets, which can be used as the reference for calculation of internal doses. The cumulated activity, as I remember previous presentation, I had left you with this question, and that is, what is cumulated activity and what is its significance in internal dose calculation? This is actually the integral of the activity present over the time interval for which the dose is to be calculated in the units of millicurie hour. So you can understand that without this kind of a data, you cannot proceed with internal dose calculations. As a formula or an equation, you can write as cumulated activity is equal to integral AS dt from time 0 to infinity. Now, you can understand that this is area under the time activity curve, that is rate of change of this radioactivity with respect to time over a particular region where you have taken the dynamic data equivalent to the renal scans, as you must have seen, and the dynamic data is used to process the or quantify the renal function. Similarly, here also it is a time activity curve, and it can be represented in this form. And the colored part is the area under the curve, and this is the cumulated activity. You can take this as the pack of infinite, minute width size rectangles packed back to back, and each of them correspond to this AS, and when you add them, that is what you get as cumulative activity. Now, what is effective half-life? First, let us understand what is half-life. It is the time taken for the substance to reduce to half of its initial amount. As for the tracer of the radiopharmaceutical which has been injected into the patient's body, it reduces by two means from the region of interest, and that is from the physical decay that is related to the radioactive part of the radiopharmaceutical, and the second one is the biological elimination which is related to the pharmaceutical part, and that is TB. From both these values, there's a formula which you can use for effective half-life, and this product upon sum of these values, TP into TB upon TP plus TB gives you the effective half-life, and you can represent it in the form of this decay curve. Now let us understand the residence time tau average life. It is nothing but the time for which the radioactivity is inside the organ or region of interest. Now the formula or decay equation you can start with, that is AS is equal to A0 into e raised to minus 0.693 upon TE, where A0 is the initial radioactivity, and in this formula for accumulated activity, if you replace the AS, it will be integral of A0 into initial into e raised to minus 0.693 upon T E into dt, T dt. And this, if you integrate and put the limits, you get the formula or equation like this, and that is cumulated activity is equal to initial activity into TE upon 0.693, and that second part is the tau of the residence time, as 1 upon 0.693 is 1.443, and tau is equal to 1.443 into effective half-life. Now from this, we can understand that the cumulative activity is equal to A0 into tau. This is what I have told you previously. And this tau can, from the previous equation, you can find it out as it is the cumulative activity upon the initial activity concentrated in the organ or region of interest at the 0 time. Now, understanding the cumulated activity can be done in this way too, and that is about A0 into 1.44 into T effective. This is what we had seen in the previous slide. And if you take the uptake time as negligible, then it will be equivalent to this mono exponential decay curve. And here, if you can put a rectangle like this, what is this rectangle? Let us understand. That is the cumulative activity actually. If you see that this cumulative activity is a product of these two values. This is the y coordinate and this is the x coordinate. Y coordinate here and x coordinate, which is plotted as the residence time. And so this exponential decay curve, which will be so much towards the infinity, and you will never be able to get the accurate area under the curve. And so this kind of geometrical shape will help to understand the cumulative activity. That is the product of these two y and x coordinates. Now for the absorbed dose, the important part of this presentation, d infinity. What is the formula? D infinity is equal to cumulated activity into S. How simple this formula looks like, isn't it? But what is S? S is the absorbed dose upon AS, or per unit cumulated activity for a given radionuclide and a source target organ pair as per MIRD. And this has been calculated using the Humanic Phantom and made life easier. And using this table as S value, you can get the internal dose calculation done. But you also have to remember about the point that the dose, if at all you want to calculate for the organ or region of interest or even the tumor, Then how much is the received dose? You want the tumor to get the maximum dose, isn't it? So you have to find out such a dose calculations also. Then the source and target organ has to be considered as the same. Now here, to understand this, what is S value? And here you can get the point of, so S value as equal to summation of delta I and specific absorbed fraction phi I. Let me call it as phi. And it has a relation between the phi, that is absorbed fraction, and this. In the few other points, I can explain that. And let us understand what is delta I. Equilibrium dose constant, and that is E into K, where E stands for average energy emitted per transformation, and K has a value of 2.13 or 1 depending on the units used for the other parameters. So if activity is in microcurie and energy in MeV, mass in grams and dose rate is obtained in rad per hour, then you have to use the value. Then the value has to be in 2.13. Otherwise, if SI units have been used, then it is 1. Now, what is this? Specific absorbed fraction. It is, you can call it as phi is equal to phi upon m. That is absorbed fraction per unit mass. If you remember, the activity, radioactivity per unit mass is called a specific activity. Similarly, this absorbed fraction per unit mass is called as specific absorbed fraction and mass of the target. Now, the summation is for the different radiations emitted from the given radionuclide. For any particular radionuclide, there may be many radiations, many types of radiations. It's not always one monoenergetic. So when it is that, then you have to sum up all these products of delta I and phi I, then you get the S value. And all this has been calculated using the humanoid phantom. Now, till now, this is about the humanoid phantoms. But then there is something which is tomographic application, and that is using a software of multiple image analysis utility. And here it is very much tailor-made for the patient-specific dose calculations. Here it is about the 3D voxel by voxel cumulated activities used in the source region based on the time-dependent radio tracer distribution of this radio tracer biodistribution from the fusion images, the SPECT-CT and PET-CT images, any of them, and getting this kind of quantification to find out the patient-specific dose calculations. Voxel is nothing but the volume element, very much equivalent to the pixel, which is the area element from the planar data. This being a tomographic or three-dimensional information to be observed, got, informed, or obtained, then that will be voxel. All this finally will give you a personalized or tailor-made pre-therapy planning. Although it doesn't come as under the roof of the MIRD phantoms, but because this is something which is more current, you have to go more deeper into this kind of tomographic application for internal dose calculation using the patient's data and making it more accurate and reaching the ground truth, as you have seen here in this picture. Now, let us summarize what I have presented, and that is one, MIRD method, the different parameters, cumulated activity, effective half-life, residence time, and the main point of absorbed dose, in which there was an S value, and then the tomography used for patient-specific dose calculation. And now I'll show you the references that I have used. And the parting question that I'm going to leave you with is as follows. Which are the conditions when the patient receives unwanted dose, and how can that be avoided? Waiting for your feedback and the questions answer. Let me take your leave. Thank you.